China is building a train that travels at 1,000 kilometers per hour, faster than most commercial aircraft fly at low altitude. And 2026 is the year we find out exactly how far this technology has come. The aviation industry has a problem. Here is everything happening right now. Hook starting with where this all began. A single train line in Shanghai that in 2004 told the world exactly what China was planning to do with ground transportation. Section 1, the Shanghai Maglev and how China built its foundation. If you have ever passed through Shanghai Pudong International Airport, you may have seen it. A sleek train gliding silently above its track, accelerating without a sound until the cityscape outside starts blurring at 431 kilometers per hour during regular daily service. On test runs, it has been pushed past 500. The Shanghai Maglev has operated continuously since 2004 and remains the fastest commercial train in regular service anywhere on Earth. What most people who ride it do not realize is that it was never the destination. It was the classroom. The Shanghai Maglev used German Transrapid technology, but China required full technology transfer as part of the deal. Engineers studied every component in detail, how the magnets generated lift, how stability was maintained at extreme speeds, how energy consumption scaled with velocity, how guideways were constructed to handle forces that no conventional rail infrastructure had ever needed to manage. That accumulated knowledge became the foundation for everything that followed. But there is a hard physical wall between where conventional maglev operates and 1,000 kilometers per hour. And the wall is not the magnets. It is the air itself. Section 2, the physics problem. Why air becomes the enemy. Maglev technology eliminates the friction problem that limits conventional rail. No wheels means no contact, no wear, no mechanical resistance between the vehicle and the track. At 400 kilometers per hour, that is a decisive advantage. But eliminating wheel friction does not eliminate the other force that grows with velocity. And at extreme speeds, that force becomes the dominant engineering challenge by a significant margin. What if instead of sending the vehicle up where the air is thin, you brought the thin air down to ground level by building a sealed tube around the track and removing most of the air from inside it? The answer to that question is the low-pressure vacuum tube system. And reducing air pressure to 1/10 of normal atmospheric levels cuts aerodynamic drag by 90%. Section 3, the vacuum tube solution and its engineering challenges. The low-pressure tube concept is not new. Engineers and theorists have discussed vacuum tube transportation for over a century. The gap between the concept and a functioning system at scale is where every previous attempt has ended. China is closing that gap through a combination of state resources, leading universities, and industrial-scale engineering capacity that no private startup anywhere has been able to match. The target is not a true vacuum, which would be prohibitively expensive and structurally complex to maintain over hundreds of kilometers. The goal is to reduce internal air pressure to approximately 1/10 of normal atmospheric levels. At that pressure, air density drops from 1.2 kilograms per cubic meter to roughly 0.12 kilograms per cubic meter. That tenfold reduction in density cuts aerodynamic drag by 90%, making 1,000 kilometers per hour achievable without energy consumption. That would make the entire system economically impossible to operate. Building and maintaining that environment over long distances requires solving problems that conventional civil engineering has never previously needed to address. The tube must be structurally strong enough to resist the pressure differential between the near vacuum inside and normal atmospheric pressure outside, across every centimeter of its entire length, continuously. Steel and concrete form the primary structural materials, constructed in sections that are individually sealed and pressure tested before being joined. Welds and connection points are the weakest elements in the system, requiring continuous monitoring and reinforcement. Hook inside the tube. The train itself runs on superconducting magnets cooled to negative 196 degrees Celsius using liquid nitrogen. And the levitation system it produces is fundamentally more stable than anything conventional maglev achieves. Section 4, superconducting technology and how it works. Conventional electromagnets generate magnetic fields by running electrical current through coils, but resistance in the wire converts a portion of that current into heat, which limits how strong the field can become before the system overheats. Superconductors eliminate that limitation entirely. Below a critical temperature, electrical resistance in superconducting materials drops to absolute zero. Current flows indefinitely without losing energy to heat, enabling magnetic fields of a strength that conventional systems cannot approach. The high-temperature superconductors used in China's new Maglev system are made from compounds including yttrium, barium, and copper oxide. These materials reach superconducting state at -196 degrees Celsius, the boiling point of liquid nitrogen. That temperature sounds extreme, but liquid nitrogen is inexpensive, abundantly available, and straightforward to handle, compared to the liquid helium required by older superconducting designs, which operates at -269 degrees Celsius and costs significantly more to produce and store. The system corrects itself without requiring continuous active control inputs, which at 1,000 kilometers per hour is a safety requirement rather than a convenience. Conventional electromagnetic suspension systems hover approximately 10 millimeters above the track surface. Electrodynamic suspension with superconducting magnets can maintain levitation at 100 millimeters or more, providing a substantially larger safety margin against any irregularities in the guideway surface. Hook, the guideway those magnets float above, must be built to tolerances of 1/10 of a millimeter, maintained continuously across hundreds of kilometers. And 2026 is when the test infrastructure to validate all of this reaches full operational capability. Section 5, the test infrastructure, and why 2026 matters. Two institutions appear consistently at the center of China's ultra-high-speed Maglev program. Southwest Jiaotong University in Chengdu has studied electromagnetic propulsion, vehicle dynamics, and low-pressure tube systems for decades, publishing hundreds of research papers and operating test facilities on campus where high-speed conditions can be simulated. The China Aerospace Science and Industry Corporation, known as CASIC, brings aerospace-grade precision engineering and complex infrastructure experience from decades of defense and space program work. Their involvement signals that this is a strategic national priority rather than a transportation project. The most advanced test track operates in Shanxi province. This facility includes a low-pressure tube section several kilometers long, where prototype vehicles can accelerate, sustain speed, and decelerate under controlled pressure conditions, while engineers monitor every sensor reading in real time. The guideway is built on pylons positioned using GPS and laser measurement systems accurate to within millimeters, with each surface section ground and polished to tolerances of 1/10 of a millimeter after curing. Even minor deviations at 1,000 kilometers per hour create instabilities that compound rapidly, so the measurement and correction process is continuous throughout the facility's operational life. Emergency braking systems have been validated at this facility. At 1,000 kilometers per hour, stopping distance stretches to many kilometers even under maximum deceleration. So the braking system combines regenerative braking that converts kinetic energy back into electricity, aerodynamic panels that deploy to increase drag, and mechanical systems held in reserve as a final option. Tests have confirmed that deceleration forces stay within safe limits for passengers across the entire stopping sequence. The 2026 target date aligns with the completion of multiple research phases and infrastructure milestones set within China's 5-year planning cycles. The test tracks reach full operational capability, prototype vehicles complete multiple rounds of refinement, and the low-pressure tube systems are proven at scale. This convergence makes 2026 the logical moment for a full public demonstration on a real route between two major cities, with limited passenger capacity focused on proving safety and reliability rather than moving mass transit volumes. Section 6, what this means for aviation. The competitive arithmetic is straightforward. Commercial aircraft cruise at 800 to 900 kilometers per hour, but that speed advantage disappears when total journey time includes airport check-in, security, boarding, transit to and from airports, and baggage handling. A flight between Beijing and Shanghai takes approximately 2 hours in the air. The total door-to-door time runs closer to 4 hours. A train covering the same 1,200-kilometer distance at 1,000 kilometers per hour arrives in just over an hour, departing from and arriving at city center stations with no security theater, no baggage restrictions, and no boarding process measured in hours. For distances up to 1,000 kilometers, the Maglev train does not merely compete with aviation. It wins on total journey time while offering a radically simpler passenger experience. The energy equation also favors the train. Aircraft burn jet fuel and generate substantial carbon emissions per passenger. A Maglev train running on electricity, particularly electricity sourced from China's rapidly expanding renewable capacity, carries a fraction of the environmental cost per kilometer traveled. As carbon pricing and environmental policy tighten globally, that gap widens rather than closes. Short-haul aviation generates substantial revenue for airlines precisely because those routes carry high passenger volumes between economically important city pairs. If a ground transport system captures even a significant fraction of that market on the densest corridors, the financial impact on airlines operating those routes is immediate and structural, rather than marginal. China started with a train it bought from Germany in 2004. It spent 2 decades building the world's largest high-speed rail network from scratch. And now it is testing a system that floats through a near vacuum tube at 1,000 kilometers per hour, using superconducting magnets cooled to the temperature of liquid nitrogen, built to tolerances finer than a human hair across hundreds of kilometers of precision infrastructure. The aviation industry spent a century building its dominance over medium-distance travel. China is building the machine that ends it. Drop a comment telling us whether you think 2026 delivers the demonstration it is promising, and subscribe, because the next update on this program is already scheduled.